The water table and groundwater are crucial yet often hidden aspects of our planet's water system. Beneath the surface, away from rivers, lakes, and the vast oceans, lies an intricate network of underground water supplies stored within layers of soil, rock, and sediment. This groundwater is an essential source of fresh water, sustaining ecosystems, supporting human agriculture, and providing drinking water for communities around the world. To begin understanding this hidden reservoir, let's start with the concept of the water table. Imagine digging down through the soil. At first, the soil might be dry or only slightly moist. However, as you dig deeper, you'll eventually reach a point where the soil is no longer just damp, but fully saturated with water. This boundary, where all the pores and spaces between particles of soil or rock become completely filled with water, is known as the water table. The water table marks the top of what we call the saturated zone, a layer where groundwater resides. Above the water table, in the unsaturated zone, the spaces between soil particles still contain air, along with some water that clings to the particles themselves. But in the saturated zone, water has filled every gap and crevice, creating an underground reservoir. The depth of the water table varies widely depending on location, season, and climate. In some areas, the water table might be just a few feet below the surface, while in others, it can lie hundreds or even thousands of feet underground. One of the fascinating things about the water table is its natural fluctuation. The level of the water table changes in response to various factors, including rainfall, drought, and the rate at which groundwater is withdrawn for human use. During rainy periods, water from the surface percolates down through the soil, replenishing groundwater and raising the water table. In contrast, during dry spells when evaporation and plant use increase, or when water is pumped from wells, the water table can drop. This fluctuation reveals just how interconnected groundwater is with the rest of the hydrological cycle. Groundwater exists because water is constantly moving, seeping, and being stored within the earth. After rain falls, some of the water runs off into rivers and streams, but a portion of it seeps into the ground. This infiltration process allows water to move through layers of soil and rock until it reaches the saturated zone, joining the vast reserve of groundwater. Once there, groundwater continues to flow, albeit very slowly, moving from areas of high elevation to lower elevations due to gravity. The speed of groundwater movement depends largely on the type of material it flows through. In porous materials like sand or gravel, water can move relatively easily, while in more compacted materials like clay or bedrock, it can take much longer. This variation in movement creates different kinds of aquifers, layers of permeable rock or sediment that hold and transmit groundwater. Unconfined aquifers are directly replenished by water seeping down from the surface, while confined aquifers lie trapped beneath layers of impermeable rock, which restricts the movement of water in and out of the aquifer. The importance of aquifers cannot be overstated. Aquifers serve as underground reservoirs, storing vast amounts of water that can be tapped through wells to provide water for drinking, irrigation, and industrial uses. Some aquifers are so large and extensive that they span hundreds of miles, supplying water to entire regions. In places with limited surface water resources, aquifers can be a lifeline, providing consistent and reliable water supplies even during droughts. However, because aquifers often refill slowly, they are also vulnerable to overuse. When groundwater is extracted faster than it can be replenished, the water table drops, sometimes to the point where wells dry up and ecosystems dependent on groundwater suffer. Groundwater's influence reaches far beyond human needs. It plays a vital role in sustaining natural ecosystems. Many rivers, lakes, and wetlands are fed by groundwater, which seeps from the earth to supply them with a steady source of water. This inflow is essential for maintaining water levels, especially during dry seasons when surface water sources may dwindle. Plants and animals in these ecosystems depend on this consistent supply of groundwater to survive. In some ecosystems, unique species have even adapted to rely specifically on groundwater-fed habitats. One of the challenges with groundwater is that, unlike rivers and lakes, it is invisible to the naked eye, making it harder to monitor and protect. This hidden nature has sometimes led to a lack of awareness about its importance and vulnerability. Pollution from chemicals, pesticides, and waste can seep into the ground and contaminate groundwater supplies, sometimes with devastating effects on human health and the environment. Because groundwater moves slowly, contaminants can remain in an aquifer for years, even decades, before they are naturally diluted or removed. Once polluted, cleaning up groundwater is difficult and expensive, highlighting the need for preventive measures to protect these vital resources. Another interesting aspect of groundwater is its role in geologic processes. In some cases, groundwater flows through soluble rocks like limestone, gradually dissolving the rock and creating caves and underground tunnels. Over thousands or even millions of years, this process of erosion can lead to the formation of entire cave systems. In karst regions where limestone is common, groundwater flow is often the driving force behind the creation of these dramatic landscapes, featuring sinkholes, springs, and underground rivers. Human dependence on groundwater has grown significantly over the past century, with increasing demand for water for agriculture, industry, and municipal use. Groundwater extraction rates have soared. In many regions, this extraction is occurring at unsustainable levels, leading to a phenomenon known as groundwater depletion. When too much groundwater is removed, it can lead to land subsidence, a gradual sinking of the ground which can damage infrastructure, reduce water storage capacity, and alter natural drainage systems. Efforts to manage and conserve groundwater are crucial for ensuring its availability for future generations. Sustainable groundwater management involves balancing water extraction with natural recharge rates, protecting aquifers from pollution, and investing in technologies and practices that improve water use efficiency. In some places, managed aquifer recharge programs have been developed where excess surface water, such as stormwater or treated wastewater, is intentionally directed into the ground to replenish aquifers. The water table and groundwater are reminders of the complex and interconnected systems that sustain life on Earth. Although hidden beneath our feet, groundwater plays a central role in our lives, supporting agriculture, providing drinking water, and sustaining ecosystems. Protecting and managing this invisible resource requires a deep understanding of how it moves, how it interacts with the environment, and how human activities impact its delicate balance. The science of groundwater is a testament to the intricate, often unseen forces that shape our planet and support life in all its forms.